Hello and welcome to a new installment of C-star algebras from a novice perspective. Today we're going to talk about the continuous functional calculus of normal elements in a C-star algebra. And this is a direct consequence of the Gelfand representation which we talked about the last time. And just to jog your memory, I'm going to get a brief recap of that right here. So previously, we talked about the Gelfand transform, which we denote by this hat symbol here, which takes an element in a Banach algebra A, in a commutative Banach algebra A, to the set of continuous functions on the set of characters on A. And we denote this map by the fact that A is mapped onto A hat here. And this map is defined as A hat evaluated at a character phi is equal to that character phi evaluated at A for any A in the algebra, and phi being a character of A, like we have here. And then we noted that the spectrum and norm of this function A hat is the same as the spectrum of A, which we have here. And this spectrum of A is actually equal to the set of functionals evaluated at A, where phi is a functional here. And then from this, we immediately get that the spectral radius of A must be equal to the infinity norm of A hat. And now here, I noted right now before starting this video that this statement is not completely true. It is true if A is a unital algebra. But if it's not a unital algebra, then you have to be a bit careful. Then the zero functional doesn't really... There are some troubles with zero functionals because normally we think of functionals as not being able to be zero anywhere. But if you have a non-unital algebra, then you can sort of have some quasi-functional that could be zero everywhere. But that would then not be part of this. And if the algebra is not invertible, then every element has zero in the spectrum. So then you have to be a bit careful. So this basically would say this spectrum here without the zero element. There can be some issues there, which we'll get into later. And then finally, we talked about the Gelfand representation once we had the Gelfand transform, once we had this spectrum and norm of A hat. Then we noted that if A is a commutative C-star algebra, in fact, then the Gelfand transform is actually an isometric star isomorphism. And this is a result we're going to use to develop our functional calculus of normal elements. So first things first, what is a normal element even? Well, if A is a unital C-star algebra, then a normal element is an element n in the algebra such that n times n star is equal to n star times n, as we have here. And note that non-trivial normal elements always exist in the algebra, as we can take, for instance, the most simple one is just taking some element A in the algebra A, and then set B equal to A star times A. Then, of course, B has an even stronger property. It's actually self-adjoint, as we see. It's not just a normal element. It's actually also self-adjoint, meaning that B star is equal to B, because this star is, of course, an anti-homomorphism. And then, of course, B is equal to B times B star because B star is equal to B, and then it's obviously normal as well. But in general, every normal element does not need to be self-adjoint, but every self-adjoint element is normal by default. And in fact, as we shall see later on in this lecture series, maybe in, say, 2 lectures, the element B, which I had here, has actually stronger properties than just being self-adjoint, which we will see later on in this video series, but not today. Today we're focusing more on how the functional calculus works for normal elements. Now, for this normal element n in A, we denote by C star n the C star subalgebra of A generated by n and n star. And basically, you can think of it as polynomials in terms of n and n star, and then you take limits as well because we want to have a complete algebra, and we want to have a Banach algebra, of course, so it has to be complete. And then one thing we note is that it's not generated by the unit element. So even though this C star n is obviously a commutative C star algebra because n and then star commute, it doesn't have to be unital because the unit does not have to be part of the generators, and if n is not invertible, then the algebra is not going to be unital in general. So this fact that this C star subalgebra is actually commutative leads us to a consequence which gives us continuous functional calculus. And we state this as a set of corollaries. So first off, if we have a normal element of the unital C star algebra A, then the C star subalgebra C star n, which we defined earlier as the set of as a C star subalgebra generated by n and its star, is isometrically star isomorphic to the set of continuous functions on the spectrum of n via a maps that takes n to the identity function. That is, it takes n to this function here, which just sends t to t. And if n is not invertible in A, then C star n is carried on to the set of functions that vanish at 0. And this is something I talked briefly there in the beginning. You noted there that if n is not invertible, then 0 is in the spectrum of every element of this C star algebra. So then the 0 functional doesn't actually exist within the set of characters. But generally, if n is actually an invertible element, then we have this statement here. Because then, of course, we know that this spectrum is, of course, a compact set always. So then we take the set of continuous functions. But here we have a non-compact set. It's actually just a locally compact set because we took away 0. And then we have to take the functions that vanish at this point that we excluded. So let's just briefly look at how we actually use the Gelfand representation to prove this statement. So first off, we note C star n is commutative, and therefore the Gelfand representation applies. That is, the Gelfand transform is an isometric star isomorphism from C star n to the set of characters on this algebra here. And we denote it by x because we don't know what it is yet. So left is to determine what x actually is. So note that if phi here is a character on A, or on the C star algebra, then it is completely determined by its value at n, which is some lambda in the spectrum by default. And that is because if we know what phi of n is, then we know what phi of any polynomial in n and n star is, because remember, a character is just a multiplicative linear functional. And then we can just calculate what this value is easily by just taking the polynomial evaluated at lambda and its conjugate. And then we note that since the algebra is dense and polynomials are dense in the set of continuous functions, then we're golden, basically. And thus, the map that takes a character to its value at n, which is also coincidentally equal to n hat evaluated at phi, that map is a homeomorphism onto n hat evaluated at the whole set of characters, which is just the spectrum. Or if you have 0 in the spectrum, then you have to be a bit careful here, but basically this is it, implying that this space is really equal to the spectrum that we began with. And also pretty clear is that this identification that we make, that identifies phi with phi evaluated at n, which is equal to n hat evaluated at phi, means that n hat evaluated at phi is identified with phi. So this identification that we have identifies n hat with the identity function on the spectrum. And then finally, if n is not invertible, then C star n is just the ideal of functions vanishing at 0. And this can be seen pretty easily because if you have 0 in the spectrum, then of course, or 0 in the spectrum of n, then if, say, a functional evaluated at n would be equal to 0, then we would use this argument to conclude that that functional would be 0 everywhere. But a functional, or this character that we're using, I should have used characters all along, really. But if a character is 0 at n, then it's 0 for every polynomial of n and n star. And if it's 0 for every one of those, then it's 0 everywhere in the algebra. But remember, characters are non-zero. And that's why we pick away this 0 point in case it lies in the spectrum. So it's basically just a technical little assumption that, or technical little detail that we have to note. But normally this is not going to bother us very much. So let's just note what we get from this. And that is that the fact that this C-star algebra is isomorphic to the set of continuous functions on the spectrum, or if the spectrum includes 0, then we have to be a bit careful about the 0, so then we get the continuous functions vanishing at 0, because then this algebra would be non-unital. And whenever n is a normal element, we can use this isomorphism here, and that gives rise to a continuous functional calculus for normal elements of a C-star algebra. And as we shall see, this is a very powerful tool which enables us to discuss some more subtle aspects of so-called positive elements of a C-star algebra, which we will get to in, I think, the next lecture and the one after that. And this theory that we get from the positive elements is what we're going to be able to use to get to the Gelfand-Naimark theorem. So let's just use the previous corollary we had and note what it gives us. So if we have a normal element and assume that f is a continuous function on the spectrum of n, then the operator f of n is defined as the inverse of f under the Gelfand transform of this C-star algebra here. Now, if 0 is in the spectrum of n and f of 0 is equal to 0, then f of n lies in this non-unital C-star algebra here. So that's something we have to take care of course. And now, moreover, we note one final thing, or two final things, and that is that the spectrum of f of n is just equal to f of the spectrum of n. So this is an expected result, it's a standard result, but it's still nice noting. And then finally, we note a result which seems trivial. That is, if g is a continuous function on the spectrum of f of n, then g of f of n can be defined as the composition of g and f evaluated at n. Because then, of course, if f is continuous on the spectrum of n and g is continuous on the spectrum of f, or f of the spectrum of n, then of course g, this composition is continuous on the spectrum of n. And therefore we can make this definition here. So note that we cannot do this for non-normal elements. We can only do this for normal elements. Because if we don't have normal elements in this functional calculus, then first off, we have to decide, okay, what does f of n mean? But once we have that, how do we determine what g of that element is supposed to be? So that is the power of this functional calculus, that it enables us to define these things in the normal way and make the functional calculus work as we would expect it to work. So let's just briefly go over how to prove this corollary here. It's really not that much of a stretch from the previous statement. So basically we just note that the first part directly follows from the previous result. And then for the second part about the spectrum of f of n, we note that the spectrum of f of n is just equal to the spectrum of f hat of n. So we take the hat of f of n. And then we note that this is of course the spectrum of f, which is just f evaluated at the spectrum of n. So this last part here, that the spectrum of f is equal to f evaluated at n, that is just the definition of the spectrum of a function. And then for the final statement, we note that this statement, of course, is immediately obvious for polynomials, because if we have defined f of n, then we can take any polynomial of that, no problem. And then for those functions, it's pretty obvious that this is well defined and that it works in this way. And then we can get the general case by approximating the continuous function g by polynomials. So it's really not a very difficult result once we have this functional calculus. And as an end to this short lecture, I would like to go over a brief taste of the power of this continuous functional calculus, because it enables us to prove many non-trivial facts about Caesar algebras in a pretty neat way, as you will see. So say that A is a unital Caesar algebra, because we want to be able to define unitary elements, of course. So if A is a unital Caesar algebra, then first off, if n is a normal element, then the norm of n is just the spectral radius of n. Okay, that's a nice statement in and of itself. And then secondly, if A is a self-adjoint element, then the spectrum of A is real. That's not obvious, but we shall see. This is actually really easy to prove with the functional calculus, while it would be kind of difficult without it. And then finally, if U here is a unitary element, then the spectrum of U is contained in the unit circle in the complex plane. So all of these three statements, they are kind of expected in a sense, but how do you actually prove them? Well, you use the functional calculus. So let's look at how we do it. First off, for the first statement about normal elements, we recall that the Gelfand transform sends n to n hat, which is basically the identity on the spectrum. And since the Gelfand transform is an isometry, we have that the norm of n is equal to the norm of n hat. This is because the Gelfand transform is an isometry. And the infinity norm of n hat, since it's identified with the identity function on the spectrum, is just the spectral radius by definition. So it's basically the eigenvalue with the highest absolute value, or whatever you want to call it, and then you get that this is rho. But it doesn't have to, of course, be a proper eigenvalue. It can be just an element of the spectrum that has this value. And then for the second statement, we can use the functional calculus again, or the Gelfand transform. Or maybe you could say that here we're not really using the functional calculus much. We're just using the Gelfand transform and the power of that. But that is basically the functional calculus. So, yeah. Anyway, if A is a self-adjoint element, then we have that the complex conjugate of A hat is, of course, the Gelfand transform of A star. But the Gelfand transform of A star is just the Gelfand transform of A, since A star is equal to A. But then we see here that the complex conjugate of A hat is just A hat, which means that A hat is a real valued function. And since the spectrum of A is the range of A hat, the second statement follows. And even if we have, say, 0 in the spectrum, then that really isn't much of an issue either, because, well, A hat of 0 will then be 0. So then we don't even run into an issue there, really. And then for the final statement, we note that if U is a unitary element, that is that U star times U is equal to the unit in A. That's why we assume that A is a unital Caesar algebra, by the way. Then the norm of U hat squared is just equal to U hat star times U, or maybe you should say the complex conjugate of U hat times U hat. But this is, of course, just the hat of U star times U, which is equal to 1. So we get that this is the hat of 1. But the hat of 1 is just the function that takes every element to 1. And the statement follows. So, to recap what we have gone over this lecture. First off, the Gelfand transform enables us to use continuous functional calculus for normal elements of a Caesar algebra. Specifically, if a function f is continuous on the spectrum of n, then f of n is the inverse of f under the Gelfand transform of a Caesar n. And then we have to be a bit careful with 0 if it lies in the spectrum, then f will have to be a function that vanishes at 0. And secondly, the continuous functional calculus behaves as expected with regards to composition. that is, if f is continuous on the spectrum of n, and g is continuous on the spectrum of f of the spectrum of, or continuous on f of the spectrum of n, then g of f of n is really equal to the composition of g and f of n, evaluated at n. And then we had that the continuous functional calculus enables us to give simple proofs of several key properties of C-star algebras, such as the spectrum of self-adjoint elements being real, such as the norm of normal elements being their spectral radius, and so on and so forth. And as we shall see in later lectures, we are going to use more of the actual functional calculus. So here we just basically use the Gelfand transform, but in the next lecture we're actually going to use the functional calculus proper to prove some really subtle properties of what we will call positive elements, which we will get to in the next lecture. And then one final thing I want to note is that the continuous functional calculus does not work for elements that are not normal. Since if A is not a normal element, then this is not a commutative algebra, which is a necessary condition for the Gelfand representation to hold. And that's it. So I think that the next lecture should come pretty soon, but who knows when it comes. Probably next week sometime. I should find the time pretty quickly, I think, now that I'm finished with grading exams and stuff like that. So until next time, have a good one. Okay, so here I'm back again. I just quickly realized that I missed to mention that if 0 is in the spectrum of n here, that is, if this C-star algebra is not unital, then we have in this corollary here that f of 0 has to be 0 for it to lie in the non-unital algebra C-star n. But we can actually define functions that are continuous even if they are not 0 at 0 for this operator n, and that is something we do by just adjoining the unit simply here. So that's something we can actually do. So if we have a unital C-star algebra A that we begin with, and then we take the normal element n here that is not invertible, and then we construct this C-star algebra, then we can actually define continuous functions that are not 0 at 0, the 0 point here, if we take care to include the unit into this C-star algebra. So you can say that then we're not using this C-star algebra, but we're using the C-star algebra generated by the unit and n and its star operator. So it's just a small detail I wanted to add. It's not really something we're going to use very much, but I just want to note that we can define continuous functions on the whole spectrum of n, or even if 0 is contained in the spectrum. And if 0 is contained in the spectrum, then we might have to join a unit to find functions that are non-zero at 0. So that's all. Now I promise I'm finished. Goodbye.